National Electrical Code requires that a grounding electrode system be installed at every service entrance to the premises. This grounding electrode system must have a minimum impedance of 25 ohms. An Ufer ground is a grounding electrode that uses the metal reinforcing bars in a concrete foundation. Ufer grounds are used when there is no other suitable grounding electrode available, such as a water pipe or ground rod. In the described situation, either of two grounding methods can be implemented. Firstly, install two separate number 4 copper Ufer grounds, one for each subpanel. Bond the two Ufer grounds together with a number 6 copper wire. Secondly, install a single number 4 copper Ufer ground. Bond the two subpanels together with a number 6 copper wire. Connect the neutral bus in both subpanels directly to the Ufer ground. The second option is typically more cost-effective and easier to implement. It also provides a good level of grounding protection for the house. Ensure that the Ufer ground is properly installed according to the National Electrical Code and local codes. If the house is built on a slab foundation, other grounding methods such as driven ground rods may be necessary. If there are any concerns, consulting with a qualified electrician is always recommended. The grounding electrode system serves as a crucial safety measure in electrical installations. Its primary function is to provide a low impedance path for fault current to return to the source, facilitating the operation of overcurrent protective devices such as circuit breakers or fuses. This process minimizes the risk of electrical shock and equipment damage during fault conditions. The National Electrical Code mandates that all service entrances, which are the points where electrical power enters a building, must have a grounding electrode system in place. This requirement applies to residential, commercial, and industrial buildings alike, ensuring a consistent level of safety across various electrical systems. The grounding electrode system typically consists of one or more grounding electrodes connected to the service equipment, such as the main service panel. Common types of grounding electrodes include metal underground water pipes, ground rods, ground rings, and concrete encased electrodes, often referred to as Ufer grounds. The NEC sets specific requirements for the size, material, and installation of these grounding electrodes to ensure their effectiveness. One critical aspect of a grounding electrode system is its impedance, which is a measure of its opposition to the flow of alternating current. The NEC stipulates that the grounding electrode system must have a maximum impedance of 25 ohms to ground. This requirement is intended to ensure that the grounding system can effectively dissipate fault current and provide a low impedance path for the current to return to the source. Achieving a low impedance grounding system is essential for the proper operation of overcurrent protective devices. When a fault occurs, such as a short circuit or ground fault, a large amount of current flows through the grounding system. If the grounding system has a high impedance, it will impede the flow of fault current, potentially delaying the operation of the overcurrent protective device. This delay can increase the risk of electrical shock, equipment damage, and even fire. To ensure compliance with the 25 ohms impedance requirement, it is often necessary to install multiple grounding electrodes or use a combination of different types of electrodes. For example, a building may have a metal underground water pipe as one grounding electrode and a ground rod as a supplemental electrode. The electrodes are connected together to form a grounding electrode system with a combined impedance of 25 ohms or less. Regular testing and maintenance of the grounding electrode system are also essential to ensure its continued effectiveness. Over time, corrosion, loose connections, or other factors can increase the impedance of the grounding system, compromising its ability to protect against electrical faults. Therefore, it is recommended to periodically inspect the grounding electrode system and perform tests to verify that it meets the NEC requirements. An Ufer ground, also known as a concrete encased electrode, is a type of grounding electrode that utilizes the metal reinforcing bars or rods embedded in a concrete foundation or footing. It is named after Herbert G. Ufer, who pioneered the use of concrete encased electrodes for grounding purposes. Ufer grounds are recognized by the NEC as an effective means of establishing a grounding electrode system, particularly in situations where other types of grounding electrodes, such as metal water pipes or ground rods, are not readily available or practical. The effectiveness of an Ufer ground stems from the intimate contact between the concrete and the reinforcing steel. Concrete is a porous material that absorbs moisture from the surrounding soil, creating a conductive path between the steel and the earth. This conductive path allows fault current to dissipate into the ground, providing a low impedance grounding path. The NEC specifies certain requirements for the construction and installation of Ufer grounds to ensure their effectiveness. Firstly, the reinforcing steel must be electrically connected to form a continuous grounding electrode. This is typically achieved by overlapping the reinforcing bars and securely fastening them together with wire ties or clamps. Secondly, the reinforcing steel must be encased in at least 2 inches of concrete. This concrete cover protects the steel from corrosion and ensures good contact with the surrounding soil. Thirdly, the Ufer ground must be connected to the service equipment with a grounding electrode conductor of the appropriate size. The size of the grounding electrode conductor is determined by the size of the service entrance conductors, as specified in NEC. Ufer grounds offer several advantages over other types of grounding electrodes. Firstly, they are often more effective at dissipating fault current due to the large surface area of the concrete encased steel. Secondly, they are less susceptible to corrosion than ground rods, as the concrete provides a protective barrier against moisture and chemicals in the soil. Thirdly, they are less likely to be damaged by excavation or other construction activities, as they are buried deep within the concrete foundation. However, Ufer grounds also have some limitations. Firstly, they can only be installed during the initial construction of a building, as the reinforcing steel must be encased in concrete. Secondly, they may not be suitable for buildings with slab-on-grade foundations, as the reinforcing steel may not be in contact with the earth. Thirdly, they may not be effective in areas with dry or rocky soil, as the concrete may not be able to absorb enough moisture to create a conductive path. In situations where a Ufer ground is not feasible, other types of grounding electrodes, such as ground rods, ground rings, or metal water pipes, may be used. It is also possible to use a combination of different types of grounding electrodes to achieve the required grounding impedance. The selection of the appropriate grounding electrode system should be based on a careful assessment of the site conditions, the building construction, and the requirements of the NEC and local codes. When running electrical feeders to a remote structure, such as a detached garage, workshop, or outbuilding, it is essential to establish a proper grounding system at the remote structure. This grounding system serves to protect against electrical shock and equipment damage in the event of a fault. The NEC provides specific requirements for grounding remote structures, depending on the type of wiring method used and the distance between the main building and the remote structure. In general, the NEC requires that a grounding electrode system be installed at the remote structure similar to the requirements for service entrances. This grounding electrode system must be connected to the grounding system of the main building, either through a grounding conductor run with the feeders or through a separate grounding electrode conductor. When running feeders to a remote structure, it is common to use either metallic or non-metallic conduit. Metallic conduit, such as rigid metal conduit or intermediate metal conduit, provides a continuous metal raceway that can serve as an equipment grounding conductor. In this case, the metallic conduit is connected to the grounding system of the main building and to the grounding electrode system at the remote structure. Non-metallic conduit, such as PVC conduit, does not provide a conductive path for grounding. In this case, a separate equipment grounding conductor must be run with the feeders to the remote structure. The size of the equipment grounding conductor is determined by the size of the feeder conductors, as specified in the NEC. At the remote structure, the equipment grounding conductor is connected to the grounding electrode system and to the metal enclosures of any electrical equipment, such as panel boards, junction boxes, and lighting fixtures. The grounding electrode system at the remote structure typically consists of one or more grounding electrodes, such as ground rods, ground rings, or Ufer grounds. The selection of the appropriate grounding electrode system depends on the site conditions and the requirements of the NEC and local codes. In some cases, it may be permissible to omit the grounding electrode system at the remote structure if certain conditions are met. For example, If the remote structure is supplied by a single branch circuit and there are no metallic paths between the main building and the remote structure, a grounding electrode system may not be required. However, it is always best to consult with a qualified electrician to determine the specific grounding requirements for a remote structure. When installing subpanels in a remote structure, it is important to properly ground the subpanels to ensure electrical safety. A subpanel is a distribution panel that receives power from the main service panel and provides overcurrent protection for branch circuits. The NEC requires that subpanels be grounded to the grounding electrode system at the remote structure. This grounding connection provides a low impedance path for fault current to return to the source, minimizing the risk of electrical shock and equipment damage. The grounding of subpanels typically involves connecting the subpanel's grounding bus to the grounding electrode system with a grounding electrode conductor. The size of the grounding electrode conductor is determined by the size of the subpanel's feeder conductors, as specified in the NEC. In addition to the grounding electrode conductor, the subpanel's metal enclosure must also be grounded. This is typically achieved by connecting the enclosure to the grounding bus with a bonding jumper. The bonding jumper ensures that the enclosure is at the same electrical potential as the grounding system, minimizing the risk of electrical shock if the enclosure becomes energized. When installing multiple subpanels in a remote structure, it is important to bond the subpanels together to ensure that they are at the same electrical potential. This bonding can be achieved by connecting the grounding buses of the subpanels with a bonding jumper. The size of the bonding jumper is determined by the size of the largest feeder conductor supplying the subpanels, as specified in the NEC. Bonding the subpanels together helps to equalize the voltage between them, reducing the risk of circulating currents and potential differences that could cause electrical shock or equipment damage. It is also important to isolate the neutral bus and the subpanel from the subpanel enclosure. This isolation prevents neutral current from flowing through the enclosure, which can cause unwanted voltage drops and increase the risk of electrical noise. The NEC requires that the neutral bus be isolated from the enclosure in subpanels except for the main service panel where the neutral and grounding buses are bonded together. To summarize, grounding remote subpanels involves connecting the subpanel's grounding bus to the grounding electrode system, grounding the subpanel's metal enclosure, bonding multiple subpanels together, and isolating the neutral bus from the enclosure. These grounding practices ensure electrical safety and compliance with the NEC. In the scenario where a 400 amp split bus meter or main panel is installed near the property line next to a utility transformer, and this panel feeds a large residence some 300 feet away via two sets of 4/0 copper feeders and PVC conduits to two 200 amp subpanels mounted next to each other in the garage, there are specific considerations for establishing a proper grounding system at the house. The question arises whether to use two separate number 4 copper Ufer grounds bonded together or a single Ufer ground with the panels bonded together using a piece of number 6 copper. Both options are viable, but the recommendation leans towards using a single Ufer ground. Firstly, consider the option of installing two separate number 4 copper Ufer grounds, one for each subpanel. In this scenario, each subpanel would have its own dedicated grounding electrode system, providing a direct path for fault current to ground. To ensure that the two grounding systems are at the same electrical potential, they would need to be bonded together with a number 6 copper wire. This bonding connection would help to equalize the voltage between the two subpanels and reduce the risk of circulating currents. Secondly, consider the option of installing a single number 4 copper Ufer ground. In this scenario, both subpanels would share the same grounding electrode system. To ensure that both subpanels are properly grounded, they would need to be bonded together with the number 6 copper wire. Additionally, the neutral bus in both subpanels would need to be connected directly to the Ufer ground. This connection would provide a direct path for neutral current to return to the source, minimizing the risk of voltage drops and electrical noise. While both options are acceptable, the single Ufer ground option is generally more cost-effective and easier to implement. It also provides a good level of grounding protection for the house. However, it is important to ensure that the single Ufer ground is properly sized to handle the combined fault current of both subpanels. In either scenario, It is crucial to ensure that the Ufer ground is properly installed according to the NEC and local codes. This includes ensuring that the reinforcing steel is electrically connected, that it is encased in at least 2 inches of concrete, and that it is connected to the service equipment with a grounding electrode conductor of the appropriate size. If the house is built on a slab foundation, it may be necessary to use other grounding methods, such as driven ground rods, in addition to the Ufer ground. This is because the reinforcing steel in a slab foundation may not be in direct contact with the earth, which can reduce the effectiveness of the Ufer ground. If there are any concerns about the grounding system, it is always best to consult with a qualified electrician. A qualified electrician can assess the site conditions, evaluate the building construction, and recommend the most appropriate grounding system to ensure electrical safety and compliance with the NEC and local codes. In addition to the grounding electrode system, it is also important to run an equipment grounding conductor with the feeder conductors from the main service panel to the subpanels. This equipment grounding conductor provides a low impedance path for fault current to return to the source, minimizing the risk of electrical shock and equipment damage. The size of the equipment grounding conductor is determined by the size of the feeder conductors as specified in the NEC. The equipment grounding conductor should be connected to the grounding bus in the main service panel and to the grounding buses in the subpanels. It should also be connected to the metal enclosures of any electrical equipment, such as panel boards, junction boxes, and lighting fixtures. By following these grounding practices, it is possible to establish a safe and effective grounding system for the remote residents, protecting against electrical shock and equipment damage.